Hey, recording is rolling. So it is Monday, March 27th. We're gonna start on electricity. So I'll do some electrostatic demos with you guys. I'll introduce you guys to these variables. You guys see a bunch of posters hanging around my room. I got a whole stack of them right here. We're gonna run through a bunch of those. Got some Paul Hewitt demos for you guys, and that'll take us to about the end of class today. Next couple weeks or so, I do have a few labs lined up for you guys that are going to involve making circuits, Christmas lights, Christmas breadboards that you guys have you guys build compost motors, electromagnet. So all this fun stuff's coming up. Let's do electrostatic demo. So we're going to be talking about point charges. What I'm going to do is I'm going to take these two. I've got two tapes taped together. Actually, let me try this. I try this new branded tape. That one worked all right, but I try this one. Okay. Two tapes taped together. I'm gonna rip these apart. Actually, oh wait. Let me precede that. Right, so that's a setup. I'm about to do that, but right before I do that, okay, let me charge up this balloon right here. You guys ever rub a balloon against your hair? Rub a balloon against your hair, right? So that'll charge it up, right? And you gotta like stick it to the wall and stuff, which I might try to do here. Now, what's going on is latex tends to want to attract electrons, and fur or hair tends to want to just get rid of electrons. Right, so that should leave a negatively charged balloon, and my hair is like positively charged. So I can stick this. Oh yeah, kind of. Yeah. Okay. Well, it'll set like right there, like stick against the wall. Is that kind of works, right? It works enough. Right. So I have this negatively charged balloon. Right. Now, charge can be positive or negative. Let me break out these tapes here. Okay. So there's two tapes. I'm going to rip them apart. Okay. Now, right now, it should just be neutrally charged, right? Like there's no like attraction or repulsion, right? But if I rip them apart, then one of these should have picked up a few more electrons than the other. So one of these is probably positively charged and one's negatively charged. Now, if I bring them back together, what should they do? Attract or repel? Should attract, right? Because they're opposite charges. See if they do. If I bring these close to each other. Whoa, a little bit too well. Yeah, they definitely want to pull together. Okay, but I wonder which one's positive, which one's negative, because they don't actually know right now. How could I figure that out? Big purple balloon. So let's see. If I hold this one next to the big purple balloon, whoa, I see a really strong attraction right there. Okay, so this one's definitely attracted to the balloon. I need octopus hands now. Okay. Which means that this must be charged how? Yeah, positive, right? Because the balloon was negative, right? The balloon's negative, so this must be positive. Okay. What do you think the other tape is going to do? Let me break out the other tape. Right, here's the other tape. What should this do next to the balloon? Should repel. Let's see if it does. Oh,
man, I got a really good view of your hand.
Yeah, well, you guys have to see it live, I guess. Here. Yeah, it's definitely repellent from it.
Does it run out?
Yeah, eventually the charge is gonna like bleed off into the atmosphere, like into the if there's like humidity, right? Different amounts of humidity. Sometimes these demos work better or worse, right? Florida's pretty humid, so eventually, yeah, the charge is gonna leak off into the rest of the world. Yeah, it definitely repels. Okay, there you go. So we got looks like like charges want to repel, opposite charges want to attract. Is what we're seeing right here. Van de Graaff. Well, hold on. Actually, yeah, okay. Let's bring up Van de Graaff. It's there's a Paul Hewitt demo on this too. So if you're watching this video at home, then be able to see that pretty soon. But we got one live in class. So you guys see this rubbery looking belt? I don't know what material it is. It might be latex. So it's kind of like the balloon, right? Okay. And there's a wire brush in here. So when I turn this on, it's going to rotate this belt against a wire brush that you can't see that's inside this bulb. Okay. And then this whatever kind of plastic or rubber latex this is going to grab those electrons. So what do you think this whole bulb is charged, positive or negative? Well, all the negatives go in here. Yeah, so this one's gonna be left positive, right? It's like losing electrons, right? I can feel it. You can feel the field, right? It's all like prickly. So I'll leave this up here about a week if you guys want to go like shock yourselves. Okay, do that too. See if you guys can see like an arc. Ooh. You gotta be at the right angle, but you guys at least hear it? You guys hear that? If you're at the right angle, you can see a purple arc. Oh, bam! Right, it's about a centimeter long. But I shocked myself. So that's there. We'll do some labs next couple of weeks. That'll be around. Guys, shock yourselves. Oh, I remember what else I was gonna do was wait, where'd the big purple balloon go? Oh, yeah, thank you. All right. I've also got this aluminum foil. Okay. Now, do you guys know that metals conduct electricity? Like the electrons can slosh around really well, right? Maybe in chemistry you learned a term called a sea of electrons. Does that sound familiar? Right. So whatever charge you put next to the aluminum, it should attract. Here's why. Like if the balloon is negatively charged, then that whatever electrons are inside the metal are going to just repel up, which leaves behind something that's positive. Right. Versus if I brought a positive charge to it, all the electrons would rush down to that. So no matter what, the metal is going to attract to whatever charge is next to it. Makes sense too? Okay, I like attract. A better version of that. There it is. Definitely attracts to it, right? Because it pushes the electrons up, the aluminum. So, right, at least one model way to think that. Okay. You guys good so far? All right. Let's go through a bunch of these posters. Oh, yeah, go. All right, so we'll do about half of these, and then I'll hit a pause point, and I'll bring up some Paul Hewitt demos, and then we'll see where we are there. Okay? So variables, got a bunch of new variables going to introduce to you guys. Okay? So one is electric charge. Now, electric charge I'm going to represent with the letter Q. It might be capital Q or lowercase q. I might use either of those. Right? Kind of like math, could be capital M or lowercase m. It's a similar idea. Okay? That's going to be measured in coulombs, right? So like a point charge, you could quantify in coulombs. I bet there's some number of coulombs that this purple balloon's charged up to, some number, right? Some charge. Right? I bet every electron has some associated number of coulombs. Right? If you can get the electric charge to flow at some rate, right, then you get an electric current. Electric current is going to be capital I, YI. I don't actually know, but I know C is used all over the place for all kinds of things, including like here's C and here's C. So I'm going to be careful with the capital letter C. Okay. But capital I is going to be current. Okay, so electric current. We're going to measure that in amperes, or a lot of times you just say amps, right? Like how many amps? What's the flow? Right? 1 ampere, 1 amp is 1 coulomb per second. Right? Oh, okay, so a lot of things in the metric system work out like this, right? One this is one that for that. Okay, so 1 coulomb of point charge per 1 second of flow, right? So it's like flowing, right? Got 1 amp. Okay. You guys might remember amperes from way back in August. I told you guys there were these like 7 fundamental base SI units, right? And this was one of them, right? So a lot of textbooks just go with like amps rather than coulombs. I don't know why, but anyway, that's what we got. Okay. Now, what causes a current to flow? Well, you have to have a potential difference, also called a voltage. Voltage potential difference. I'll use those interchangeably. You can measure that in volts. Right? What is 1 volt? It's like energy per unit charge, it's like joules per coulomb. Okay? And if you look on a battery, every battery has an associated voltage, a potential difference. Do you guys happen to know what the voltage is on a AA battery? AA? Right now? Ooh, good guess. That's the multiple of that. Right? I got is it focus on there? 1.5? Yeah, 1.5 volts. Okay, this 1.5 volts. Now, you can put a bunch of these in series. You can get 6 volts or 9 volts or 12 volts because those are all multiples of 1.5. Yeah, just a single AA battery. Yeah, 1.5 volts. Okay. What if you get one of these boxy type batteries? How many volts is this guy?
9.
It is 9. 9 volts. 9 volts right there. I see 9 volts. Okay. What about your car battery? How many volts your car battery?
300?
About 12. About 12 volts. Yeah, 12 volts. Okay. Just easy to like start the car and get it going, right? Okay. All right. Okay. Another idea here. Resistance. Now, here, have you guys ever taken, say, like a bare wire or a paper clip and unwound the paper clip and it just attached the positive directly to the negative? You guys ever done that? Who's done that? Who's done that? Right. Yeah. Well, what happens to the battery? Yeah, it gets really hot really fast, doesn't it? Right. And it drains it really fast. I mean, maybe if you were out camping, you could even start a fire with it. Right? Hey, I need to start a fire. Hey, I've got like a paper clip and a battery. Okay. But it does drain the battery really fast, doesn't it? Because all the energy, because that wire has almost no resistance, almost none of this resistance. Okay, just a bare wire. Right. And ideally in a circuit, you actually do want some amount of resistance. So it doesn't just like drain your battery in like 2 minutes. Right. So right. So we'll look at some resistors. Right. You can measure resistance in ohms. It also breaks down like this if you like that. Okay. Now, if you have a resistor on a circuit and you pop in your battery, it'll cause a current to flow. Right. And hey, I wonder what's the rate of that energy flowing? Oh, well, that's what power is measured in watts, which is something you guys remember from last semester, right? 1 watt is 1 joule per second. You guys remember that, right? You don't even need amps or coulombs or anything for that, right? But maybe you buy a light bulb that says like 40 watts on it. Oh, well, that means if you plug into like 120 volt outlet, which is what we have in this room, is here in the States, 120 volts, right? That bulb has a resistor in it that would produce this particular power output, that wattage. Okay? You guys okay so far? Okay. It's a bunch of new ideas here. Now, it gives you kind of a yellowish background on these top 5. Right? Those are the main ones that we care about. Now, as we go on through the class, I'll also introduce you guys capacitors and inductors. We'll just touch on those, but we're not going to really deal a whole lot with them. Okay, but I'll tell you guys a little about them in the future. Right? Okay so far? All right. Next slide. All right, here's Coulomb's law. So this is just point charges. There's no electricity flowing, but there are like some charges floating around, right? Okay. So we're talking about the electrostatic force here. Maybe we should put a little subscript E on this for electrostatic force. Okay? So what's the electrostatic force between 2 point charges? Well, Q is like a charge. Remember, I told you guys it could be capital or lowercase. In this case, lowercase. Right? So we're going to multiply the 2 charges together, divide by the distance between them squared, and multiply by this constant. Ooh, does that look a lot like universal gravitation? It does look a lot like universal gravitation, doesn't it? You guys remember the force between like the Earth and the Moon or 2 asteroids could be GMM over R squared? You guys remember that? This looks just like that. It's the same format. Okay, inverse square law with force and distance. Okay, whole deal. Okay. Now differences between electrostatic force, which is what you're looking at here, versus universal gravitation. One is that universal gravitation only ever attracted. You guys remember that? Gravity only attracts. Okay? But electrostatic force can be attraction or repulsion. Like if I have a positive and negative, you guys saw, and you guys told me already anyway, that's going to attract because they're opposite charges. So they're going to attract just like I drew it here. Okay. But what if it was positive, positive? Would those just push away from each other? Yeah. And that would still follow this, but it would just be repulsion. It would just push away, right? But the magnitude of the force would be the same, right? Another difference between electrostatic force and gravitational force has to do with the magnitude. Like you guys remember for GMM over R squared, that capital G, universal gravity constant, that was like 10 to the negative 11, which is a tiny, tiny, tiny number. It's like 0.000, so a string of zeros, right, before you get to any digits. Okay? Versus this electrostatic constant, it's like 10 to the 9. Ooh, that's like a billion of something. That's a huge number, isn't it? So just generally speaking, what do you think is the more powerful force, electrostatic force or gravity? Electrostatic. It's not even close, right? We're talking about like crazy orders of magnitude stronger, right? In fact, I can prove it right here. Bam, that proves it. Right? Here's why. There's 2 forces on this pin. There's its weight pulling down. That's like the gravity force trying to pull it down to the center of the Earth. Okay? But then this normal force from the surface, bam, brings it to a dead stop. But what is that normal force? Well, if you get down to it, it's really just electrons on the surface of the paper pushing against electrons on the surface of the pin. Right? So electrons against electrons. That's electrostatic force right there. Right? And that's beating gravity every time. Right? All right. Let's get that charge flowing to create a current. But remember how you do this is you're gonna put a voltage source, right, on a circuit. So I might attach some leads of a circuit here, but maybe I want a resistor too, right? Here's the symbol for resistor. You just use jaggedy type, right? Now, when I first learned electricity way back in the day, this confused me for a couple of weeks. I couldn't wrap my mind around it because everything's invisible, right? Like what is voltage? What is current? Like I can't see any of this stuff. But then I was taught this analogy, and this is where it all just like clicked in place, and it finally made sense. Okay? So whenever you see voltage, think like pressure. So a battery is kind of like a pump, like it's trying to pump electricity through a circuit. Okay? The resistance that the electricity faces, think of it kind of like a crimp in a pipe. So if you have like water flowing through a pipe, okay, it's kind of like a crimp in the pipe, which you do want on a circuit. You do want there to be some resistance so it doesn't just drain your power source. Okay? Right, and as a result of these two guys in conjunction with each other, there'll be some flow rate, right? And that's current. So current measured in amps is analogous to flow rate that could be like gallons per minute flowing through a pipe system, or maybe cubic meters per second, like a metric system, right? Is that true? Right. So let's look at. Okay, I got some stuff about resistors, and then we'll put together with Ohm's law. Okay. So how much resistance is in a wire or maybe a resistor? Well, here's that relationship. So the amount of resistance, say from end to end, right, has to do with how long it is, the length. Like if it's 3 times as long, do you think you get 3 times the resistance? Like what if you have a wire that's 1 kilometer long versus if it was 3 kilometers long? 3 times the length, you guys think 3 times the resistance? Kind of makes sense, it would be, right? That's a direct relationship. But what about this cross-sectional area? What if you have a little skinny wire versus a big fat wire? What do you think is easier for the electricity to flow through? Little skinny wire or big fat wire? Big fat wire. Yeah, that's what the electricity wants to flow through. So the larger the cross-sectional area, the less the resistance, right? Does that make sense? There's an inverse relationship between these two guys. Right? Now, one last detail here is resistivity. So Greek letter rho in this context represents resistivity. That's to say, what if you have a copper wire versus an aluminum wire? Do you think electricity is going to flow differently through those? And that's what this is. That's this resistivity. Okay, right, that makes sense. I do have a lab on those, so I might have you guys do this lab next couple weeks. If you look at resistors on a here, I've got a little breadboard here. Right here, let me show you this breadboard real fast. Right, so where the term breadboard comes from is when circuits were first being put together, probably about 200 years ago or so. Okay, they would physically use these wooden boards that were used to cut bread on. So they would actually break out. Oh, let's grab the breadboard from the kitchen. And they'd start drilling a bunch of holes in them and like hooking a bunch of resistors and like the rudimentary batteries to them. Right. And they realized after doing so many of those, well, you know, we just need to like manufacture these things. So they finally just put a bunch of holes in it, and there's some metal wires on the back side of this that I'll show you guys too. Right, and then you could just like plug stuff into it. Here I've got a little LED light, right, which has like some resistance in it, but you can plug in all kinds of stuff, right? You can plug batteries into this. You can plug in resistors. I got an LED here. Capacitors, inductors. You can wire up all different kind of circuits for all different kind of things. You can make little robots with these things. Okay. So let's look really fundamental at a resistor. Resistors look like this. They have these colored bands on them. You can actually read the colored bands, and I'll tell you exactly what the resistance is. So I got a brown band, which represents the digit 1. Green represents 5, and then this red is 2. But in this context, it's 10 to the power 2. So it's 1500. That'd be ohms, 1500 ohms. And this gold band is tolerance is plus or minus 5%. So there you go. It's 1500 ohms plus or minus 5%. Okay. You might plug that into a breadboard. This is like one of your components. Okay. Here we go. Here's Ohm's law. Here's what we care about. Right. So we got our battery here. Here's our voltage source battery. Now the symbol for that is just 2 parallel lines, one shorter than the other. So this could be my battery right here. Bam. The longer side is the positive terminal, which is like this in a battery, and then the short side is the negative. That's like here. Okay. And then I got my resistor. An example of a resistor could be a light bulb, right? Doesn't have to be, it could be, or maybe it's that resistor that I just showed you on slide right here. Okay. And then as a result of this, there's going to be some current that flows through. Capital I is current. Okay. And this is what Ohm's law says. Voltage, like 1.5 volts, I can on some resistance, boom, get a current flow in some number of amps. Okay. Is that all right? Okay. Then Joule's law. So what is the power flowing? Right? Like how many watts? Watts of power. Okay? And here's 3 different perspectives on Joule's law. Okay? So you can do current times voltage, but you can also substitute in Ohm's law. Right? Say like, what if you only knew the voltage and the resistance? Like I know what battery I'm hooking up, and I know what the geometry of my circuit is, so I know these two. Right? You substitute in Ohm's law, and you can get this version of it, or if you like, you can get this version with the current. Okay, so these are all saying the same thing. They're all 3 different perspectives on the same idea. Right? And I'm going to show you guys one more slide, and then we'll switch over to Paul Hewitt, although I have a bunch of other posters left too, but we're going to save some of these for the future. Oh, yeah, go ahead. Oh, yeah? Yeah. You write that down. Okay. So power in watts could be current times voltage, or depending on what knowledge you're starting out with, it might be more handy sometimes to use one of these other 2 versions of it. Okay? So you go to power is current squared times the resistance, or you could do power is voltage squared divided by the resistance. Now, that could be for an entire circuit. You could do like from the point of view of the battery, like the entire circuit, the electricity that's flowing through. Or you could do individual components. You could dig into a circuit. If you have a really complex circuit, you say, well, what's going across like this particular resistor? And you could do it that way. Okay. So we'll switch back and forth. We'll do both perspectives. I tend to approach circuits from a macro point of view, saying what's going on with the battery first, and then figure out from there. Paul Hewitt, you guys see, he likes to look at each individual resistor and just add it up like from a micro approach. Okay. So with both those. All right, here's the last one before we switch over to Paul Hewitt. Remember how a battery is analogous to a pump? Whenever you see a battery, think pump. Voltage, think like pressure. And a light bulb could be an example of a resistor, right? It's like consuming the electricity, sort of, right? That electricity, the electrical energy is being converted to like light and heat, right? And there's some rate that's happening. So power is equal to current times voltage. That's one version of Joule's law that I just showed you guys. Right? And that actually works exactly with this analogy. So what's the rate of energy, say, with this water wheel? Right? Well, that could be the flow rate of the water, like in gallons per minute, or in this case, cubic meters per second. How about that? Because the units actually do work out perfectly for us, right? Cubic meters per second. Right? And multiply by the pressure. Like, do you guys think if you have a really deep dam compared to a really shallow dam, the really deep dam, you're going to get more pressure and more energy from that, right? But if it's 3 times as deep, you get 3 times the pressure, therefore 3 times the power, right? There you go. And so these units work out too. That times that does give you some number of watts. Okay. Nice, good back. Oh, I forget if I mentioned it. I did upload all these slides. Right. So yeah, we've gone through about half of them. I still got another half to go through. Right. Uploaded all these to Google Classroom over the weekend. So you guys have these there too. Okay. And of course, they're all hanging around the room. All right. Right. Next one. Oh, oops. I was going to show you guys this too. Let's just do this one real fast. Right. Flashlight schematic. So a schematic is just a representation of one of these diagrams. Right? So battery, voltage source, yeah, looks like that. Right. A light bulb is an example of a resistor. Not all resistors are light bulbs, but light bulbs are examples of resistors. Right. And then what does a switch look like an on-off switch? Right. Well, you could switch this off. Let's say you break open the circuit. That's turning it off. Right. Or if you switch it on, that'd be like closing the circuit so the electricity can flow. You guys see, for the electricity to flow, you have to have a connection from the positive and negative leads have to attach. Right? You guys see that? Right. Small detail I want to mention too. Let me go back a few slides here. Right? Has to do with the direction of the flow of current. Right? Now, nowadays, since it's the 21st century, we understand that there are electrons that move. Like if you attach a battery to anything, you get a direct current, which means that the electrons flow like from the negative terminal to the positive terminal, right? Makes a loop. Those electrons physically move, and then they move really slowly. It's something like millimeter per second, something like they move really slowly, right? But the charge flows, right? But when electricity conventions were first being crafted back in like Ben Franklin's day, they didn't actually know that. They just knew there was some kind of movement of charge. So they just did a coin flip, and they defined the flow of current as the flow of positive charge. See how it looks like it's going from the positive terminal to the negative terminal? So the convention just follows the flow of positive charge. Nowadays, with our updated modern understanding, we know it's actually electrons that are moving. So it's like the opposite of what's going on. But that's okay. Whether you do flow of positive or negative charge, mathematically, it's all equivalent. Okay. So it's just one of those little quirky details. Okay. All right. Next one lined up was I start talking about series and parallel. I'm going to save that. So let's flip over and look at Paul.